This conference will now be recorded.
Hello everyone. Physical properties for haloalkanes and haloarenes we have already started. We'll finish it today, and then there will be discussion related to, that is, the problems related to basic physical properties, and after finishing that we will see the preparation methods for haloalkanes and haloarenes. Fine. So last day we have started melting point and boiling point trend. So some points we have already covered, and see, after finishing fourth point in this slide, that is the last slide in last class. Now the fifth point, here we have among isomeric alkyl halides. Suppose you have 3 to 4 alkyl halides and all are isomer to each other, that is same number of carbon, halogen and hydrogen. Now what will happen? The boiling point will decrease when there is increase in the branching in the alkyl group. Fine. So here we will see example. This is linear chain, that is the first one. And how many carbon atoms are there? It is 1, 2, 3, 4. 4 carbon. Number of hydrogen 9 and 1 Br. So same molecular formula it is also for the second molecule and also for the third molecule. But what is the difference? As we are moving from 1 to 2 to 3, branching is increasing. With increase in branching, what will happen? Now the molecule will be more in spherical type of shape. Because if you look at the first molecule, it is linear chain, right? But the second one, now it is comparatively less linear and more spherical. And the last one, when branching is even increased, now it is more towards spherical shape. So when it is having more and more spherical shape, that means surface area is less. Because keeping the volume same, if you consider any shape, only in case of sphere, there is minimum surface area. So that is why when we are moving from 1 to 2 to 3, as it is becoming more and more spherical in nature, so that is the reason its surface area is very less. Now, when surface area is very less, the intermolecular forces, it will become very weak because that is directly proportional to the surface area. And when intermolecular forces are becoming weak, that means boiling point will also be low, because to separate the molecules, to increase distance between the molecules, you don't have to provide very high energy. Just providing low energy, you can easily convert them from liquid state to vapor state. And that is actually the boiling point. That means boiling point will decrease. So look at this value, it is 375 Kelvin. Now it is lesser than this 364 and the next one 346. So as we are moving from 1 to 2 to 3, the value is becoming less and less. Fine. Next, if you have haloarene, and what type of haloarene? Suppose you have dihalobenzene. Now this dihalobenzene, its positions may be, as there are 2 halogen, the positions may be ortho, meta or para, that is 1, 2, 1, 3 or 1, 4. Now all of them are isomeric because same number of halogen, carbon and hydrogen we have. So they are isomers, only difference in the position of these 2 halogen. So they will have almost similar boiling points. That is, with respect to boiling point, there is not much difference. But if it is melting point, now you can see the difference. So here we have example. 2 chloro, they are at ortho position, then meta position, and the last one para position. Look at the boiling point. 180, 173, 175. So there is not much difference. But if you consider melting point, it is minus 17 degrees centigrade. But the next one, it is minus 24. So it is not just decreasing, but the difference between these two, that is also high. And the last one, that is the para. Now it is not even minus. So there is drastic change in the value of melting point. Now what happens in case of melting point? Melting point means the change of physical state from solid to liquid. That means crystal structure we have to consider. When it is para isomer, that is 1,4 substituted, that is the last compound. Among these 3, the most symmetrical structure is this one, because it is 1,4 symmetrical structure. So because of this symmetry, now what will happen in the crystal lattice? It will fit in a very good way. So as a result, when fitting is better in crystal lattice, so obviously to break the crystal, now you have to provide very high energy. That means now melting point becomes high. So para-isomer, because of its symmetry, fits in crystal lattice better as compared to the ortho and meta-isomer. And this will lead to very high compact crystal structure, and to break this compact crystal structure we have to provide very high energy, and that is why the melting point value, if you look at this value, it is highly different from these two. It is not just positive, but also compared to this the value is itself very high. Okay, so this 5th point and 6th point both are related to some isomeric structure, but the first one is for aliphatic, the second one is for aromatic. Next physical property after boiling point and melting point is density. Now density, how it is related to mass and volume? Density is mass divided by volume, that is mass per unit volume. So density increases with increase in number of carbon and halogen atoms and atomic mass of halogen atom. Look at the first box. Here we have compounds. These three compounds, they are basically derivative of methane. If you replace 2 hydrogen with 2 chlorine, you will get CH2Cl2. If you are replacing 3 hydrogen, you will get CHCl3. And if you are replacing all the hydrogens, you will get CCl4. Now, as we are moving from more substituted methane derivative, density is also becoming high. Now, what happens here? When you are moving from CH2Cl2 to CHCl3, then CCl4, it is true that mass is increasing, because compared to hydrogen, now you have H replaced by Cl, so mass obviously will increase. So overall molar mass is increasing. So here numerator and denominator, if we consider, M is increasing. That means D will also increase. But it is also true that volume is increasing, because compared to the size of H, now the size of Cl is high. So as you are moving from CH2Cl2 to CHCl3 to CCl4, volume is also increasing. So this denominator, that is also increasing. But you have to remember that M is increasing, V is increasing, but the overall increase is such that there is overall increase in D. That means the increase in the value of M, that is compared to the decrease in increase in volume of V, because when both are increasing, there should not be any effect on D. D should be same. But here the rate of increase of mass and the rate of increase of volume, if you compare, obviously the rate of increase of mass is high, which is overcoming the increase in the value of volume. So overall, that is ultimate effect is that D is increasing. Okay, so that is why this type of effect here we can see increase in density. Then the next example, C3H7Cl. So here alkyl part same, we are only changing the Cl. So here also same logic you have to apply, because D is proportional to M, D is inversely proportional to volume. Now when volume will increase, that means density will decrease, fine. And when mass is increased, density is directly increasing. So when we are moving from the Cl derivative to Br to I, obviously molar mass is increasing. Alkyl part is same, but you are changing the halogen. And halogen, its atomic mass is increasing from Cl to Br to I. Now there is increase in mass, and also there is increase in volume, because compared to the compared to the volume of Cl, obviously the volume of Br is high. But that effect is overcome by the increase, by the effect of increase in the mass. So as a result, the overall effect on the density value is such that ultimately when you are moving from Cl to Br, it is increasing. When you are moving from Br to I, then also it is increasing. Okay, so this is all about density. Number 5th point, haloalkanes, their solubility. Now these compounds, that is haloalkanes, that is RX, in general if we write the structure, they are polar covalent molecules. Polar covalent means this bond between carbon and halogen, it is covalent bond, that is fine. But remember, X is very highly electronegative compared to carbon. So that is why there is some polar nature also present. And the positive, partial positive charge over carbon, negative over halogen. So there is also some polar nature. That is, it is not bond between two similar atoms. There is difference in electronegativity. So though it is covalent bond, but still there is some polar nature. So haloalkanes are polar covalent molecules, and it is observed that they are soluble in organic solvent, but they are not soluble in water. Now the reason is they cannot form hydrogen bond with water molecules. Fine. So this is the first reason. But why they are soluble in organic solvent? Haloalkanes tend to dissolve in organic solvent because the new intermolecular attraction between haloalkanes and solvent molecule have much the same strength as the one being broken in separate haloalkane and solvent molecule. So what is the meaning of this? Suppose before dissolving RX to the solvent, you have individual RX and there is some interaction present. Similarly, when you have any solvent molecule, suppose I am writing it with S. So between two solvent molecules, there is also some interaction. But when you are mixing these two, now there will be a new kind of interaction, which is the interaction between RX and the S molecule, that is solvent molecule. Now the old interactions, that is this one and this one, and the newly generated interaction, this is newly generated. If the newly generated interaction, it is having almost same strength as the original old interactions between two RX and between two S, if they are almost having same strength, so now this strength can be broken, that is this interaction can be broken, this interaction can be broken, so that a new kind of interaction between RX and S is now possible, and that is why it is soluble in organic solvent. So they have the same strength, almost same strength as the one being broken in separate haloalkane. Separate haloalkanes, this is separate haloalkane, this is separate solvent molecule. Okay. So whenever you are considering any solubility, suppose you are trying to dissolve A in B. So before addition of A to B, there is individual A molecule and individual B molecule. So this AA interaction or BB interaction and the newly generated interaction, which is AB, this newly generated interaction must be equal to or greater than the old interactions, then only solubility is possible. Okay, so same logic applies here. Now after solubility, here we will see this problem. Arrange the following compounds in the increasing order of their densities. Here we have simple benzene molecule, monochloro substituted benzene, dichloro substituted benzene, and 1 bromo, 3 chloro. That means this is also dihalo, but now one halogen is Br, another halogen is chlorine. And what we have seen when we have discussed density trend, remember in the last slide, when you are moving towards higher atomic mass halogen, that is, look at the first table, when there is 2 chlorine and then you are moving to 3 chlorine and then 4 chlorine, that is when number of halogen is increasing, density is increasing. So according to that logic, 3 should be having more density than 2, 2 should be having more density than 1, right? And when 1, 2 and 3 there is 2 and 3 there is only Cl, 1 there is no halogen, it is simply benzene, and number 4 now 1 Cl is replaced by Br. And look at the second table in this slide, when you are moving from one high atomic low atomic mass to high atomic mass halogen, then also density increasing. That means if you compare 3 and 4, obviously 4 will have higher density. So it is very simple. 4 maximum, then 3, then 2, and then 1. So this is the correct option. Maximum 4, minimum 1. Next problem, which of the following compounds will have highest melting point? Remember when we have discussed melting point, then in case of haloarene, higher is the symmetry in the molecule, higher is the better is the crystal structure packing because of symmetric nature. And when crystal structure it is having very compact nature, obviously melting point will also be high. Now among these three, the common point that you can see in every three, that is all the three molecules, there is 2 methyl group at 1 and 4 position. This is constant. Same in all these. So with respect to this methyl, you cannot give any expansion. But if you look at Cl, here 2 Cl, they are at 1 and 2 position. This is at 1, 4 position. These two are 1, 3 position. So among these three, obviously this is the most symmetric. So that is why here you can expect compact crystal structure. So melting point, that will also be high. So this is the correct answer. The structure 2, as it is having symmetrical nature, so that is the reason it will have highest melting point. Fine. So after finishing physical properties and related problems, our next topic will be preparation methods of haloalkanes. So see here, the heading is preparation method of haloalkanes, because the methods that you will use for the preparation of haloalkanes, it is not necessary that it will be same also for haloarene. So it will be different. So that is why under separate heading, we will discuss the synthetic methods for preparation of this type of organic halide molecules from alcohols. So here our starting material will be alcohol. So basically from ROH, now you will be making RX. And there is not just single method, so many different types of reagents are available for this type of conversion. And you can use any of them, though that depends on what type of alcohol is there or what type of RX you are trying to make. But different reagents are available, but we have to use them according to the what kind of molecules are present as starting material and what is the nature of your final product. Alcohols can be converted into haloalkanes by reacting it with any one of the following reagent. So look at this reagent, you can use HX. HX means HBr, HCl like this. That is hydrogen halide. Then PX3, that is PCl3, PBr3, then PCl5 and thionyl chloride, HOCl2. Now another method is there which is known as groups method. So in this method what we do, we use ZnCl2 and this is actually acting as catalyst. And what is its purpose? Its purpose is to weaken the carbon-oxygen bond present in alcohol. But if it is 3-degree alcohol, that is the alcohol from which you are making the haloalkane, if this alcohol is tertiary, then you don't need any ZnCl2 because it is going through SN1 mechanism, and in SN1 mechanism the carbocation that you will get from 3-degree carbocation is very stable. So easily carbon-oxygen bond can be broken. For that you don't have to use any separate catalyst. So that is why it is mentioned here, ZnCl2 is not required. So look at this. This is the general structure of alcohol. The first method is groups method, where you are using HCl plus anhydrous ZnCl2 which is acting as catalyst. But remember, for 3-degree you don't have to use this catalyst. And this reagent mixture is also known as Lucas reagent, and this test sometimes also called Lucas test. So from ROH, now what we are getting? We are getting RCl. Next method, constant boiling with HBr, which is 48%. that you can use if you want to make RBR. Now directly HBr, it is not necessary that directly you have to use HBr. You can also use mixture of NaBr and H2SO4, because when it is acidic medium H2SO4 and NaBr is there, so from NaBr easily HBr can be generated in the reaction medium, which is actually the actual reagent. So OH is replaced by Br. Then PX3, as it is mentioned here, then PCl5 and SOCl2 pyridine. Now when you are using SOCl2, pyridine is also added. Now what is the purpose of this extra reagent? Because SOCl2 should be enough, but pyridine we add because it is basic in nature. So as it is base, so it will try to remove this byproduct HCl. So when the byproduct is removed, according to Le-Chatelier principle, if a system is already in equilibrium and you are changing some conditions like concentration, pressure, volume, then the system will try to counteract this effect that we are coming from external source. So what will happen when HCl is consumed by pyridine? This HCl it is produced in the right hand side, so the equilibrium will be shifted more towards right hand side than left hand side. So as a result, more RCl will be produced. So this is the reason that pyridine is used to consume this HCl, which is the byproduct, side product. If we want to get good yields of Ri, that is alkyl iodide, then what we can do? We can heat the alcohol in presence of sodium iodide or potassium iodide. Just like, see here you have used NaBr because your purpose is to make RBr. But if you want to make Ri, now you will use the iodide salt, that is sodium iodide or potassium iodide, and in acidic medium. So here we have taken H2SO4, but when it is Ri that you want to make, now you can take 95% H3PO4, which is also acid. The reactivity order of halogen acid, HI, HBr, HCl. That means, suppose from ROH you are trying to make RX, and this RX, when it is HI, it is Ri, when it is HBr, it is RBr, when it is HCl, it is RCl. So, keeping all other conditions same, this is the reactivity order of halogen acid. That means, if the alcohol is same, when you are using HI, you can easily get the corresponding iodide product compared to HBr and HCl. So this is the order. Then we have Darzen procedure, which is basically the procedure here it is mentioned. Mixture of pyridine and SOCl2 you are using as reagent. It is a base method for preparing alkyl halides from alcohols. Now why we are calling it base method? Because here the byproducts that are generated is sulfur dioxide and HCl, and both are gaseous in nature. So their removal, the process, that will be very easy. So when side products can be removed very easily, obviously the separation of actual desired product, this is your actual desired product, not SO2 and HCl, they are byproduct. So you have to separate them, right? But if they can escape so easily, obviously this method will be very good. Okay, and don't think that HCl is liquid. HCl actually not liquid. When it is pure HCl, it is actually gaseous. The HCl liquid in bottle that you see in laboratory, that is actually its aqueous solution. But HCl actually it is gaseous molecule. So that is why both of them are gaseous. Here from the arrow sign also you can understand both of them are gaseous, they can escape easily. So that is why this method is very good for preparation of alkyl chloride, because SOCl2 when you are using, obviously you will get RCl, not RBr or Ri. But remember, all these methods are not applicable for the preparation of aryl halide. That is, these methods you cannot use for haloarene. Why? Because the CO bond in phenol. Because when you will prepare haloarene, obviously now you will not take alcohol, now you will take phenol. Obviously, phenol we have to take. Now, phenol, the lone pair over oxygen, it can take part in resonance with the double bonds of benzene ring. So as a result, what will happen in the resonance structure, there will be some carbon oxygen double bond character generation. So because of this double bond character generation, now breaking of this bond, carbon oxygen bond, that will be very difficult because of this partial double bond character. Because compared to single bond, breaking a double bond, that is obviously difficult process, right? So as there is partial double bond character generation, it is difficult to break as it is stronger compared to a single bond. So when it is alcohol, you can easily break this carbon oxygen bond, but that is not possible in case of phenol, and that is the reason you cannot use all these methods if you want to make aryl halide, that is haloarene. So that we are, as I have already mentioned, that we are discussing these preparation methods for haloalkanes and haloarenes separately, because this is aromatic in nature. So the methods that will be applicable for haloarene, obviously that will not be useful for haloalkanes. Okay. So the first method that we have seen, our starting material is alcohol. Next, now we will use alkane as starting material. And this method is free radical halogenation. So here alkane, generally we can write the structure as RH, and you are converting it to RX. And this is free radical halogenation. That means it will follow radical mechanism. RBr and RCl, if you want to make, their formation is possible by free radical halogenation. So see, look at this example. Here we have taken propane, C3H8. Then in presence of chlorine and H nu, there will be replacement of this H with chlorine, which is 55%. But it may be also that these terminal hydrogens are replaced by Cl, which is 45%. Now instead of chlorine, when you have taken bromine, keeping the other conditions same, now you will get again the mixture of 2 bromopropane and 1 bromopropane. But see, now the selectivity compared to the previous situation, now it is better. It is almost 1:1, right? But it is very good. It is almost 100% and 0. So obviously, if you want to make RCl or RBr, better, that is RBr you can easily make by this method, because when it is RCl, you are getting mixture and you have to separate this mixture, right? Radicals are highly reactive intermediates, because here as the mechanism is going through radical, single electron is present. We know that radicals are very reactive intermediates. So when the intermediates are very reactive, obviously selectivity is less, because selectivity and reactivity, these two are inversely related. When something is very reactive, that means it is very unstable. And if something is unstable, it will randomly give different types of product. If some species is stable, then only it can give some selective major product. But if the intermediate itself is so unstable, that is highly reactive, obviously you cannot expect selectivity. So they are basically non-selective in nature, which you can easily see in this molecule. So here we have taken very simple structure, which is propane, CH3, CH2, CH3. But with this simple structure, you are getting this type of ratio, 55-45, almost 1:1. So when the alkane is very complex, then difficulty will also be very high, because higher is the complex nature of this initial that is starting material, I mean the alkane. Obviously different types of hydrogens will be there, and all possible monochloro derivatives will be produced, and separating them individually, if you want to get all these molecules, it is really difficult. Okay, so it will basically form a complex mixture of isomeric, not just monochloro. See, with monochloro you are getting two types of isomer. Now there may be dichloro substitution, then polychloro substitution, polyhalo in general if we say. So it is really very difficult to separate these pure compounds. So that is the reason it is not a very preferred method if you want to make haloalkanes. So though we should know this method, but remember, compared to the previous method, which is where we have used alcohol as the starting material, obviously in this case separation of the products will be very difficult. So look at this mechanism. Starting material we have taken methane, very simple. Then in presence of chlorine and light or H nu, first H is replaced, you are getting chloromethane, but other hydrogens may also be replaced. So this method, it will not stop here, it will continue. Now next you are getting dichloromethane, then trichloromethane, and ultimately all the hydrogens are replaced. So there is a complex mixture. Starting with methane, how many products you are getting? 1, 2, 3, 4. Okay, so it is difficult to control the reaction because it is under going through free radical mechanism, which are really highly unstable, and that is the reason selectivity is very less. So this is not a very good method for the preparation of haloalkanes. Is there any doubt? So this method that is just we have just seen, that is starting with from alkane, you are making haloalkane. Based on this, we have a question here: how many chiral compounds are possible when you are doing monochlorination? So it is clearly mentioned that it is monochlorination. That means only one hydrogen will be replaced by one chlorine. And monochlorination of which compound? It is 2-methyl butane. Okay, so butane is this molecule, and at 2 position there is methyl group. So this is the structure. Now in these molecules, how many different types of hydrogens are there? Because if there are 3 types of hydrogen, obviously 3 types of product formation possible. If there are 4 types of hydrogen, 4 types of monochloro compound you will get. Fine. Now if you look carefully, these two CH3 group, total 6 hydrogens are there. So all these 6 hydrogens, they will have same kind of nature. So any of these hydrogen can be replaced by Cl and you will get similar product. Then the second type of hydrogen is this one. Suppose it is A type of hydrogen. This is B type of hydrogen. Now these two hydrogen, it is C type. And this methyl group at the right hand side, suppose it is type D. So when you are, that is how many different types of product you can get? Total 4 types. So what you will do, first you will write all the possible products. Here from this compound only 4 products possible, but that is not always. It may vary depending on what kind of alkane is given in the question. So what you will do first for this type of reaction, you have to draw all the possible structures and then look carefully whether there is any chiral center present or not. If there is no chiral center present, they will not be chiral compound. So first you have to draw all the products, then only you can understand. Here, this is 2-methyl butane, 1, 2, 3, 4. So these 2 methyl groups, all these 6 hydrogens, as I have mentioned, it is type A. So if these hydrogens are replaced by Cl, you are getting this type of compound, which is compound number 1, product number 1. Here, this center, there is a star sign given, that means it is chiral. Why it is chiral? Because here with this carbon, you have CH2Cl group, methyl group, and ethyl group, and hydrogen. 4 different groups are present, so this is chiral. Next, if you are replacing this B type of hydrogen, then you are getting chlorine here. Now look at this carbon. It is containing 2 same group, and third group is chlorine, fourth group is Et. So this is not chiral, right? Now if you are replacing this C type of hydrogen, you are getting again a chiral center, because in this carbon, the groups that are present is isopropyl group, Cl, H, methyl. So this is also chiral. And the last one, when you are removing D type of hydrogen, now here you do not have any chiral center. So only compound 3 and 1, these two are chiral. And the question that is asked here, how many chiral compounds are possible on monochlorination? So it is obviously option A, only 2 compounds are possible. Fine. Any doubt?
No, ma'am.
Next one. Here the question is related to alcohols, where alcohol is the starting material and from alcohol you are trying to make alkyl chloride. It is asking which of the following alcohols will yield corresponding alkyl chloride when you are treating it with concentrated HCl at RT, room temperature. Then which of these 4 alcohol, because all these molecules given in option 1, 2, 3, 4, all from all these alcohols you can get alkyl chloride, but the question is which will yield the corresponding alkyl chloride with concentrated HCl at room temperature. So it means that for all these alcohols it is not possible to produce the corresponding alkyl halide at room temperature, because room temperature is 25 degrees centigrade, and reaction is possible from ROH. You are making alkyl halide at room temperature, means that means you are not giving any further external temperature is not given. So the alcohol must be highly reactive, then only room temperature reaction is possible. Because if the alcohol is not very reactive, you have to give some temperature, but you are not giving any temperature. It is at room temperature, but still reaction is happening. So it means the question is trying to say you have to find that alcohol which is most reactive to yield the corresponding alkyl halide. And the first alcohol, it is CH2CH2CH2H, and the carbon with which OH is attached. This carbon is attached to only one carbon, so this is 1 degree. Then the next one, option 2, the carbon with which OH is attached, that is attached to 2 more carbon. That means this is 2 degree. Option 3, the carbon with which OH is attached, that is attached to only one carbon. This is also 1 degree. But the last one, the carbon with which OH is attached, that is attached to 3 more carbon. So this is 3 degree. And what we know, when you are making RCl, that is because you are using HCl. So obviously you are making RCl. Starting from the alcohol, it is undergoing that is SN1 mechanism. If you consider 3 degree alcohol, it will give best result because it is going through the 3 degree carbocation, which is very stable. So that is why the last alcohol, as it is 3 degree, that will give the result, that is it can yield the corresponding alkyl chloride at room temperature. So correct option is 4. Fine. Next method. So 2 methods we have seen. The first method is you are using alcohol and then from it you are making haloalkane. And for this conversion there are so many methods are available, and this is a very good method actually. Then the second method that we have seen, where we have started from alkane and by free radical halogenation we are getting alkyl halide, but because of its highly reactive nature this is not a very good method. Now from alkene, so this is basically number 3 method, where the starting material is containing CC double bond because it is alkene. Now under this heading you have some methods. So number 1 is addition of hydrogen halide. Hydrogen halide means HX, it may be HBr, HCl, Hg. And starting material is alkene. So CC double bond must be present. Alkene can be converted to haloalkane by an electrophilic addition reaction. Now why we are calling it electrophilic addition reaction? So suppose you have any alkene. Suppose in general I am writing the structure R2C double bond Cr2 and you are treating it with HX. So what you will get? CC double bond, now it will be it will not be present, and there will be CX bond and CH bond. So as HX is added to this CC double bond, so that is why it is addition reaction. Okay, added. But why it is electrophilic? Electrophilic means what? The reagent is electron deficient. So here first what happens, H is added to CC double bond, and here pi electron density is present because there is a pi bond. So this alkene will behave as nucleophile, and the reagent that you are using, in this reagent, H is basically the electrophile, because first in presence of H plus, which is coming from HX, the double bond will be attacking this H plus. That means now one of the carbon is protonated. So here alkene is giving electron density towards H plus. So H plus is basically the electrophile. Electrophile, how we write it? E plus. And alkene is basically the nucleophile. So as the reagent is electrophilic in nature, so that is why the name is electrophilic addition reaction. Fine. Alkene reacts with HX to form RX. The mode of addition follows Markovnikov rule. And this rule basically will help you to understand the regioselectivity. Now what is regioselectivity? See here the alkene example I have just shown, R2C double bond Cr2. This is basically symmetrical, right? Both sides same group. So when you are added HX, you don't have to think which side you will add X, which side you will add H, because it is symmetrical. It doesn't matter anything. But that may not be the case always. Suppose the alkene is not symmetrical. Look, propene. Is it symmetrical? No. Left hand side 2 hydrogen, right hand side 1 methyl H. Now the question arises whether X will be in the right hand side carbon or left hand side carbon. So there are two possibilities. In the first product, you can see halogen is added to the right hand side carbon. But in the second possibility, halogen is added to the left hand side, and it is written here, it is major 97%, this is minor. So how to understand whether how we will understand which one is major, which one is minor? And for that you have to take the help of Markovnikov rule. And it is regioselectivity because these two compounds, suppose it is number 1 product, this is 1 prime. So among 1 and 1 prime, these two are basically regioisomer. Regioisomer means same number of all atoms, but position, that is region where the Br is attached, that region is different. That is why it is regioisomer. So as there is a possibility for generation of two different types of regioisomer, so that is why it is regioselective reaction, because among these two possibilities, you are getting one as major. One is greater than 1 prime. So that is why it is regioselective. And Markovnikov rule will help you to understand this regioselectivity. But I will suggest, don't just blindly follow Markovnikov rule. Try to understand why Markovnikov rule, that is, what is the actual logic behind this rule. But first we will see what is the rule. According to this rule, whenever there is unsymmetrical alkene and you are considering electrophilic addition reaction, so in addition reaction of this unsymmetrical alkene, the negative part of the reagent, so here our reagent is HBr, negative part means Br minus. Now why we are calling it negative part? Why we are not calling it halide? There is reason for that. Here we are discussing HBr addition, but if you want to make this rule more in broader sense, if you want to use, better you use the term the negative part of the reagent, because in some books you may find it is mentioned as the halide will be added to this carbon or that carbon, but I will suggest use this type of line, that is the negative part of the reagent. So here H and Br, obviously Br is the negative part. If it is HCl, Cl is the negative part. But suppose the reagent is not HBr, suppose the reagent is ICl, then what you will do? Because both are halogen. Now look carefully. Chlorine is more electronegative than I. So ICL, it is basically analog of HCl, because here also chlorine is more electronegative than H. ICL chlorine is more electronegative than I. So here also it is negative part, here also it is negative part. So always it is better you use the more general form of Markovnikov rule, so that it can cover a wide range of different types of reagent. Okay. So it is saying that the negative part of the reagent, it will attach itself to that carbon which is containing lesser number of hydrogen. So suppose it is carbon number 1, this is carbon number 2. Carbon number 2 is containing lesser number of hydrogen. So bromine will be attached to that carbon. So that is why it is the major product. But you can keep in mind this rule. But why it is actually occurring, that you have to understand. As I have mentioned here, that first step is attack towards this H+. Now if the attack is happening in this way, there is two possibility. The first possibility is, if protonation is happening at carbon number 2, then the positive charge will be generated at carbon number 1, like this, CH, CH3, CH2, CH2, because protonated. And if protonation is happening at carbon number 1, now it will be CH3, CH3, now positive charge here. But among these two carbocation, this one is more stable because it is 2 degree. This is 1 degree. So as it is giving you 2 degree carbocation, so that is why when the negative part is now added, this will give you this product number 1. But from 1 degree you are getting I2. So that is, it is a minus. But remember, Markovnikov rule will be successful as long as there is no rearrangement. But if there is a chance of rearrangement in the carbocation intermediate, then Markovnikov rule, simply following the Markovnikov rule, you will not get the correct result. Okay. So in this case, as it is very simple unsymmetrical alkene and there is no chance of rearrangement in the carbocation, but suppose in some cases it may happen that the carbocation, there is some rearrangement is going on. So when there is rearrangement going on, the carbocation itself will change. So don't then simply follow blindly Markovnikov rule. Then you have to write this proper mechanism step by step. You have to reach towards the actual answer. Okay. Now come to this question, which is related to HBr addition to alkene. The increasing order of boiling point of the major product A, which you are getting from first reaction, B, major product which you are getting from second reaction, C, that you are getting from the third reaction. So see, this question is very interesting because it is combining basically two questions. It is asking about the increasing order of boiling point of ABC. That means it is related to physical property of haloalkane, because ABC, all these are haloalkane. You are adding HBr to alkene. But first you have to know what is the structures of ABC. Then only you can compare their boiling point. You can write the order of their boiling point. So this question is basically combination of two questions. And first you have to consider electrophilic addition. Then you, once you already know the structure of ABC, then you can write their order of boiling point. But here one unusual thing you can notice, there is a reagent given only for option number, not option, only in the first reaction. And what is this reagent? C6H5COO. C6H5 means pH. If I write it elaborately, it will be pH CO, then another oxygen, and as it is coming twice, so it will be like this. Now look at this molecule carefully. This is containing peroxide linkage, and whenever you are doing HBr, that is electrophilic addition towards alkene in presence of peroxide, now anti-Markovnikov rule will be followed. So when it is Marconic of, what you have seen, negative part is added to that carbon which is containing lesser number of hydrogen. But when it is anti-Marconic of, it is just reverse. So when it is in presence of some peroxide compound, not necessarily it has to be pH, this peroxide only. General structure of peroxide, it may be like this, that is ROOR. Now these two are, it may be anything, but important thing is peroxide linkage must be present. So if this type of compounds are there, then it will be anti-Marconic of rule that you have to follow, because now the mechanism is not ionic mechanism. In the previous slide what I have shown you, that it is ionic mechanism. First there is formation of carbocation and then addition of Br minus is added. But when you are, it is peroxide, it is basically radical mechanism, completely different mechanism. So that is why now it is anti-Marconic of rule. And remember, this peroxide, this is known as peroxide effect, and peroxide effect, it is only applicable, peroxide effect only applicable for HBr. If it is HCl or HI, whether you use peroxide or not, it doesn't matter anything. It will give you anti-Marconic of only for HBr. Okay. So in the previous slide, just see, suppose this propene, if you take the molecule again, H2C double bond CH. This is propene, and here we are adding HBr. You are getting one as major, but suppose if you are doing this reaction in presence of peroxide, now the major product will be I prime. Okay, so be very careful in the arrow whether peroxide is mentioned or not, only for HBr, that you have to be careful. Now come to the actual problem. So for the first reaction, as there is peroxide present, and among these two carbon, this is containing two hydrogen, number 1 carbon, number 2 carbon containing only one hydrogen. So according to Marconic, this should be the carbon where Br should be attached, but as it is following anti-Marconic, so Br is attached to one carbon, not two. So this is the structure of A. Then the second molecule, here H and Br, one carbon there is no hydrogen, two carbon there are two hydrogen. So Br will be attached to number 1 carbon because it is containing lesser hydrogen, actually zero hydrogen. So that is why this is the structure of B. And the last one, it is symmetrical. It doesn't matter anything. That is Marconic of rule. You don't have to take care of it. So this is the structure of C. Now you know the structure of A, B, C. So you can compare their boiling point. So these three molecules are basically isomer. Why? Because see, these alkenes are isomer. This is, all these alkenes are containing 4 carbon. 1, 2, 3, 4. 1, 2, 3, 4. So A, B, C, all these are basically isomer, right? Same number of carbon, hydrogen and bromine. And in the first slide of today's class, remember what we have seen, that when there are isomers, higher is the branching, lesser will be the boiling point. So here maximum branching is present in B. So this will give you minimum boiling point. And minimum branching is present in A. So it will have maximum boiling point. And C is in between. So this is order A, C, then B, which you can find in option 1. So this is the order of boiling point. Any doubt? Should I repeat? Then under this heading, that is from alkene, after finishing the first point, which is addition of HX, next method is addition of halogen. That is, now you will add directly bromine or iodine or chlorine. Addition of bromine, it is normally done in organic solvent CCl4, 2L-ankine, and what you get vicinal dibromide. Vicinal dibromide means, remember, adjacent carbon will contain halogen, CBr. So that is, it is vicinal. If it is same carbon containing two halogen, it will be gem dihalide. But this one is vicinal dibromide. In short, VIC written. So when it is symmetrical alkene, as you can see here, 2 bromine, which is having some reddish color, but after addition of these 2 bromine atom to CC double bond, now the color of bromine will be discharged. That is, suppose you are adding bromine from some test tube towards 2 alkene, the color of bromine, it will be now colorless. So which is basically some visible change you can observe. So from this observation, you can understand that some CC double unsaturation is present. So that is why bromine color is discharged. So this is basically the identification test for an organic compound to understand whether there is unsaturation present or not. The reaction involved discharge of reddish brown color of bromine. So that is why this is the identification method for double bond, whether it is present or not. Now, next we have halogen exchange. Halogen exchange, under this heading, you have 2 types of reaction. One is Finkelstein reaction, next one is Schwarz reaction. Finkelstein reaction is SN2, and Schwarz reaction, here SN2 mechanism is followed in the first case. So first we will see what is happening here. Finkelstein reaction, chloro or bromoalkane. So from alkene, 2 methods we have discussed: addition of HX, addition of halogen. After finishing it, next we are moving to the 4th method, which is halogen exchange. Now from the name you can understand here halogen will be exchanged by some other halogen. So in the first method, suppose you have started from chloro or bromoalkane, you are heating it with a concentrated solution of NaI. So Cl will be replaced by I, and it will give you iodoalkane. Now NaCl or NaBr, that will be formed as byproduct, and it will be precipitated in triacetone because they are not soluble in acetone. So these 2 are byproduct. It will be precipitated, which you can easily separate, and it is also facilitating the forward reaction. That is, as the byproduct, when byproduct is not soluble, it actually helps to move the direction of the reaction from left to right according to Leach atelier, because initial NABR, they are precipitated, they are not increasing the concentration of the solution, they are precipitated. That means equilibrium will be easily shifted from left to right. So this is the example. You have started from chloroalkane, bromoalkane in presence of NaI and triacetone. You are getting Ri, and these 2 are precipitated because you are not using water. And NaCl, NaBr, they are soluble in water, but it is not water, it is acetone, organic solvents. That is why they will be precipitated. And the second method is synthesis of alkyl fluoride. Now this method is only for alkyl fluoride, and it is best accomplished if you are heating an alkyl fluoride or bromide in presence of some metallic fluoride. Now you can take any of these reagent. You can take AgF, Ag2F2, cobalt fluoride, or SbF3. So all these are metallic fluoride. So see the example. We have taken the first reagent. For this example, you have started from methyl bromide in presence of AgF. Br is exchanged by F because it is halogen exchange. You are getting CH3F, Ag and Br together, it is making the byproduct AgBr. So here the mechanism is SN2. So these 2 are the methods under halogen exchange. Some more preparation methods we will also see in the next class. So in today's class, if there is any doubt, please mention. Okay, so we are ending the session here. Thank you for listening.